Hello, I welcome you to the next tutorial for microwave testing. This is a method to non-destructively test parts made from glass fiber reinforced plastic GRP and other non-conducting materials. If you want to learn how this method works, then you are right here. This is the handheld probe FMH4 for microwave testing. This antenna, which we see here, is a rectangular opening in the flank, the rectangular opening of a rectangular metal pipe, which is called a waveguide. The microwave is an electromagnetic wave. The electrical field is this opening is just in parallel to the narrow side of the opening, and the magnetic field in parallel to the broad side of the opening. This insert shows the field distribution and field strength in the opening. The radiation field in front of this antenna, the electrical field of that is just directed in that direction, which is also in the waveguide itself, so mainly vertical in this case. And that leads to special phenomena of this so-called polarization effect. And we will see some of these phenomena in the following. This is a plank from high density polyethylene, HDPE. The permittivity is about 2.4. On the bottom side, we have inserted 3 artificial defects. The one is a short length of a metal wire. The second is the insulation of it, which we may call a dielectric wire. And then we have a small round metal washer. So we have 2 pieces which transverse to the main length of the plank, and 1 round element here. We will do the test from the top side, that means here, here and there, and see what happens. Now I place the probe onto the plank and move it across the metal wire. We see a strong deflection. I move it back, and we note that we had the orientation of the probe such that the electrical field was in direction of the wire. Now I turn the probe around so that the electrical field is perpendicular to the wire, and we see a deflection, but considerably smaller than before. So with electrical field in the direction of the wire is a stronger signal than before. That not only holds on a metal wire, but also on a dielectric wire. And we will see that right now. I place the probe onto the plank before the dielectric wire and move it across the dielectric wire. We see the deflection. I move it back to repeat it. That was with the electrical field in parallel to the dielectric wire. Now I turn the probe around and I repeat the movement. We see a deflection, but is considerably smaller than before. That means also here the signal is stronger when the electric field is in the direction of the wire. To have a counter test, I now move the probe over the washer, the metal washer, and we see a very strong deflection with the electrical field in the direction perpendicular to the length of the plank, and I go back. Now I turn the probe around with the electrical field now in the direction of the plank, and we see the deflection in the same order of magnitude. Well, from this experiment we have learned that defects which are not round can better be detected when the probing field is in parallel to the length direction of the defect's shape. However, in practice, one often does not know the shape and the direction of the search for defects. In such cases, it is recommended to test with both polarizations. So far, we have seen what happens due to the direction-dependent electrical field of the probe. And we note that we did the experiment on HDPE, which is a material with properties which are the same in all directions. However, in general, the device under test may have directional dependent properties. An example is the unidirectional glass fiber reinforced plastic GRP. In this material, the glass fibers, are all in one direction. Then the effective permittivity is higher in the direction of the glass fibers than perpendicular to it. And even round defects may give different signals when probing with different polarizations of the probing field. Let's look to an example. Here we have a section of a GRP leaf spring, which indeed is unidirectional. The rovings of the glass fibers are all in horizontal direction. And we see a very shallow, small, blind hole here, and we will move the test head across this round defects, the test head with two polarizations, and we will see what happens. I place the probe on the GFRP leaf spring before the flat hole with the electrical field now perpendicular to the fibers, and I move it across the hole. We see a very slight deflection. I go back and we see the small deflection again. Then I turn the probe around such that the electrical field is in the direction of the fibers, and I repeat. I move across the flat hole. We see a distinct deflection, and I go back and we see the repetition. Well, we have learned that round defects in electrical anisotropic material give stronger signals when the probing electrical field is in the direction of the higher permittivity. So far, we have seen the application of the FMH4 with its planar antenna on parts with planar surfaces. In the next tutorial video, we will see how the probe can be applied to pipes and further curved surfaces, and that without tilting and wobbling effects by use of special adapters. That's it for today. Thank you for watching. Goodbye.